So we have covered a lot of things in this course so far, including how to realize the power converter, then some sections on this, how the PWM can be, that part we will see, but at least AC to or DC to AC power conversion, we have seen slightly with the help of SPDT switch and how to realize the SPDT switch. So now the important part is when you are generating, let us say you have the three-phase system, three-phase VSI, and for simplicity we will take two level and VSI because this is the common structure used in most of the industrial drives nowadays. So we will take one leg of this converter. There are two switches. Okay, of course, anti-parallel diode is there, is part of the switch. Now we have seen that with respect to point O, VRO we are trying to generate the simplest possible. Let's say this is plus VDC by 2 and this is minus VDC by 2. The simplest possible way to convert the DC to AC is simply have the switch S1 connected for time period T by 2 and then the switch S2 connected for time period another T by 2. So this cycle repeats over the period, this interval T. So here you are connecting S1, here you are connecting S2, and say if this total cycle we say that the angle is 2 pi, so then this is our half cycle up to this. We are having positive plus VDC by 2 and here we are having minus VDC by 2. Now to understand that what we are actually generating, whenever we are generating any this kind of inverter voltage, obviously it is little bit far from the fundamental. It's not exactly sinusoidal. It's actually pretty far from the sinusoidal input voltage. So first we need to understand that what are the different voltages which are present in this kind of waveform, and assuming that this is repeating in the same manner always. So we are maintaining this cycle time period which is T and we are switching in the same manner. So pi, 2 pi, so on it is going. So this may be 3 pi and this may be 4 pi. Like that it is going on. So every 2 pi you are repeating this waveform. Now the simplest way to understand what components are present in any periodic waveform, we know already that it is like Fourier transform. So Fourier analysis suggests that any periodic waveform can be represented in terms of sinusoids. Sum of many sinusoids will actually form this waveform which is visible over here. This we know from our prior experience. There is nothing much to say, right? Now, if I have, let us say, to express this, say this is VRO. So if I have to express VRO theta, it can be written as or let us take it cos first. So cos n theta. Oh, it's repeating. Correct. So here the coefficient Bn is there. So there is a reason why I'm writing 2 over here. So then we can maintain uniformity. Let's say this component what is present over here is generally the DC component or the average component. And these are the various sinusoids, or you can say harmonics, including the fundamental. This is what these terms are representing. Now we can express these coefficients A0, A1, Bn in terms of what voltage we have and different what we are trying to generate. So A naught is basically this, the average of VRO over this one cycle. So when I'm writing 2 over here, basically I'm trying to keep uniformity with what we are dividing over here. So then AN can be written as 1 by 2 pi 0 to 2 pi VRO theta cos n theta d theta, and Bn can be written as 1 by 2 pi 0 to 2 pi VRO theta sin n theta d theta. Like that, we can express all the coefficients of different harmonic components, including DC, fundamental, everything. And this could be the general representation of all the coefficients. Now here, as I said, you might have seen somewhere that this is 1 by pi, then this 2 would not be there. So I am keeping this 2 over here because I am keeping this denominator uniform for all the three coefficients. Understand the point?
Yes, sir.
Okay, so don't get confused.
Yes.
Now, what I want you to do is that do a quick computation of this waveform, which is given over here, and tell me what are different components you are able to see in this. What is the magnitude of, let us say, the DC and then fundamental, the second harmonic, third harmonic, and so on. Okay. So you may take some time. Now let us see what all components are there. So this VRO we will express as, again, whatever I have written. So some DC plus whatever harmonics are there. So this harmonics include first, second, third, and so on, all the harmonics. Okay. So I'll keep the expression on the screen so that it is easier for you. And waveform you know already. It is plus VDC by 2 over here up to pi, and then minus VDC by 2 for the next half cycle. So let's start with the DC component first. Then we go for fundamental, that means A1 and B1, and then we go for the second harmonic, third harmonic, and so on. Okay, do we have some answers?
A0 is coming 0.
Okay.
AN also 0.
A not 0.
DC is coming to be 0. Where is A naught? There is, okay, the DC component you are saying.
Yes.
This is coming out to be 0. Okay. Then
AN is also 0, sir.
AN in general is 0. Okay. What else?
AN 0.
Yeah. So two things we have identified. So basically this is now limited to only VRO being equal to summation of 1 to infinity, say 2Bn. So Deepak, how is it going?
Yes, sir.
How is it going?
Sorry, sir, your voice is little low.
You have a lot of noise on your background.
One.
Sir, Bn is VDC by n pi for n is odd, and for n is even, it's 0.
For n even, this is 0. This is what we are getting, right?
Yes, sir.
For everybody?
Yes, sir.
Yes, sir.
Okay. So what we are seeing over here, that when we have this square wave waveform, this is, say, if we talk about the fundamental component only, it is basically coming out to be isn't it? This is what your fundamental component is, right? Any other harmonic, when you talk about VRO n, this is coming out to be 2VDC by n pi sine n theta, where n is basically odd and n is greater than 1. In fact, this is true for n equal to 1 also, but I'm just writing it separately. Now let us say that you have to run your motor from inverter and you are generating this kind of voltage. So you are bound to have a fixed voltage unless you change your DC bus voltage. You understand this point? You have a fixed fundamental component which is coming like this. Notice that VDC by 2 and this is minus VDC by 2. So this peak is basically 2 VDC by pi. Okay. So slightly higher than your this VDC by 2 because this is higher than VDC by 2. Now this is what you are getting as fundamental. In this form, basically we can operate the motor at only one voltage unless we change the DC bus voltage. So if we want to generate something like variable voltage, variable frequency, this kind of supply, then we have no other option but to change VDC. And which is very difficult because DC bus voltage means it will have lot of no time constant. So it may take several seconds before you get any change or something. Particularly when you are dealing with bigger motors, no high this voltage systems or medium voltage systems where DC bus voltage is very large, it becomes very difficult to change it suddenly. So certainly we need to have something more in this waveform. So let me introduce one more factor in this waveform. Say near the 90-degree angle, we switch it once. Okay, and same is repeated, say near the 270-degree angle. Now, say this is pi by 2, this is pi, this is 3 pi by 2, this is 2 pi. Now, little bit difficult exercise for you. Now, can we identify what are the different components in this waveform? So basically this waveform is switching at alpha degree and it is going to minus VDC by 2 from alpha to beta, where beta is more than 90 degree, and then it is coming back to plus VDC by 2. And same on the negative half cycle, we have a transition from minus VDC by 2 to plus VDC by 2 at gamma, and then at delta it is coming back to minus VDC by 2. So this is little bit more involved, but this will open up lot of things for you. So now can we have the numbers, let's say A0, AN, BN and so on.
Sir, A0 to 0.
Don't jump on conclusion, Sampan. First write the expression, see what you are getting. I have not said anything about alpha, beta, gamma, delta, all this, right? Have I said anything?
No, sir.
Maybe a bit of exercise for all of you before your exam.
A naught is coming VDC into 2 alpha minus beta upon 2 beta.
Little loudly.
So VDC into 2 alpha minus beta upon 2 beta.
VDC into
2 alpha minus beta
2 alpha minus beta
upon 2 beta.
Say again.
Upon 2 beta.
Divided by 2 beta.
Yes, sir.
How is beta coming here?
So sorry, beta. Sir, I have taken integration from the time constant 2t instead of 2 pi. I have taken the time from 0 to beta.
0 to beta is which time period, Ajay?
After that, this
Waveform
signal.
is same.
Yes.
Sir, VDC by 2 pi into alpha minus beta minus gamma plus delta.
Alpha minus beta
Minus gamma plus delta.
minus gamma plus delta. This is what we are getting, right? Okay. What about AN? Anyway, just compute what is A1. Don't worry about AN if it is difficult, or if you can get AN, that is also fine. Whatever is easier, just get some expressions.
Sir, VDC by 2 pi into like I computed only for AN.
Yes, yes.
VDC by 2 pi into sorry, sine alpha minus sine beta minus sine gamma plus sine delta.
Is this correct? Is this correct? This is for A1, right?
Yes, sir.
Yes,
Good.
sir.
Hmm.
Yes, sir.
Okay. Other expressions? A2, for example, and then B1 and B2. So you are considering VDC by 2 over here, right? And not plus VDC and minus VDC.
Yes, sir.
Good.
सर सेम रहेगा, एक्सप्रेशन सेम है, बट अल्फा की जगह 2 अल्फा, बीटा की जगह 2 बीटा हो जाएगा.
So there must be 2 all here also.
Yes, sir. Denominator.
D1, B2.
Sir, Bn is BDC divided by 2 pi n. Minus cos n alpha.
Okay.
Plus cos n beta.
Okay.
Plus cos n gamma. Plus cos n gamma.
And then minus cos n
That's
delta.
minus n delta. Then plus 1 minus cos
Plus 1
n pi. Minus
minus
cos n pi.
cos n pi.
Pi. Yes. So for n equal to odd, it will
Yes.
become plus 2 and n equal to.
Okay, good. So we have expression for B completely. So everywhere we have n, right? Cos n alpha, n beta, n gamma, n delta, and then this also coming as n pi. So we have considered all the harmonics. Good. Now,
And
few things you try to notice over here, that if, let us say, you make alpha equal to beta and gamma equal to delta, so ultimately it should come back to your square wave. So this is first check for your expression whether it is correct or not. you should get the previous value if you do this, alpha equal to beta and gamma equal to delta. So let us quickly see if that is happening or not. So your A1, A0 will become 0. There is no doubt in that. If that is the condition, this all cancels out. Here also, it will cancel out and this will become 0. Even A2 also, because this is symmetric, so we can generalize AN as this, and this also becomes 0. Now, Bn, if we see, if n is odd, so then this value goes to, what will be the value of this? This will become plus 1, right?
Minus.
Plus one.
Yeah, total minus cos n pi will become plus 1.
Yes.
We have plus 1 over here. Now, every other thing will cancel out because this is again equal. Plus minus, this combination will come out. Here we have 2. So, what we will get is 2 VDC by pi. For n equal to 1 we are having, right? I think somewhere you have missed this VDC by 2. Otherwise, this would have come. Here it should be 4 pi, I think.
Yes, sir. Should be 4. Yes, sir.
This should be 4 n pi. So you have to consider VDC by 2. So B1 will come back to this value 2 VDC by pi when you plug in these values as alpha equal to beta and gamma equal to delta. Basically, you are not switching, going back to square root. This is one check whether your expression is fine or not. So then I think I can correct all the values. So here also there should be 4 pi. Here also there should be 4 pi. Now, basically what we are trying to do when we are generating any waveform and we are taking the Fourier transform, what we are trying to do basically, we are trying to take out the components which are already present in the waveform. If it is not present, then it goes to 0. What is meaning of that? Let us say you have a simple signal, which is basically sine omega t. Okay, this is something like, and the magnitude is say A. Sinusoid is there and you are trying to take the Fourier transform of this. So what we will do basically say this signal is x. X is nothing but a sine theta. Now we are trying to take Fourier transform. So what we will do, we will multiply cosine of n theta and sine n theta and take average and all that. So basically what we are trying to do, when we have purely sinusoidal waveform, which means it is balanced on the positive and negative half cycles. Let's say here, whatever positive value you have, exactly equal negative value is on the other side. Then we will certainly see that the DC value is going to be 0. And which is what is there. If you take this average, x d theta 0 to 2 pi, so this will turn out to be integration of a sine theta d theta 0 to 2 pi, which will be minus cos theta, and the average value will be 0. You understand the point? So by keeping equal values on both the halves, we are ensuring that there is no DC component. Secondly, when we are multiplying with sine theta or cos theta, what is basically happening? Let us see. When you multiply with sine wave with magnitude 1, say this is your sine theta. So this product will ultimately become what? It will become a rectified sine wave kind of structure. And then you are trying to take the average of this black waveform. So if exactly this waveform is coinciding or matching with the given waveform, which means if that particular harmonic is present, then only you will have a DC value over here. You understand this point? So basically, if you multiply sine theta with a sine theta and integrate this and take the average, so what you will see basically over here, only when these two are having the same nature, that means same frequency as well as same orientation. only in that case you will find non-zero value over here. If you have, let us say, two waveforms which are having different frequency, and you try to take the product, say a sine omega 1t, and you take it with another frequency, say omega 2t, and you take average, this will certainly become 0. You understand the point? This will be non-zero only in condition omega 1 and omega 2 are equal. Then Bn is going to be non-zero. The meaning is same. If you try multiplying, let's say, third harmonic with this waveform, what you will have basically, this is third harmonic wave. And how the product will come out, say blue waveform, if I draw, it will come out to be positive and then negative and then positive, something like that it will go. Something like that it will be. Understanding my point? So wherever this is negative, this will basically bring it down. And now the average value of this new blue waveform is obviously 0. You have equal positive and equal negative. So whenever there is mismatch in frequency, if whatever frequency you are trying to multiply, if it is different from what is present in the waveform, then certainly this product is going to be 0. Also, let us say if there is a waveform which is of the nature sine omega t, and you are trying to multiply it with cos omega t, what you will have basically, again you will have a double frequency waveform coming over there. You understand the point? There is sine theta and you are multiplying cos theta. This is basically nothing but sine 2 theta by 2, which is a double frequency waveform. So you will have something like which is going at double rate. So okay, let me draw in black. So this will be 1 and this will be other. This is the resultant and maybe magnitude will be half. So in effect, when you try to multiply different sinusoids, which means a sine theta with a cos theta, you are getting again a balanced waveform which is having equal positive and negative values. And what average it will have? 0. You understand my point? So what I'm trying to say, when we are analyzing any waveform, let us take example of the square wave, what we have taken earlier. We got average value equal to 0, obviously because we have balanced voltages on the positive and negative side. Up to 2 pi. So up to pi you have this plus VDC by 2, and then for this another half interval you have minus VDC by 2. So when you see that it is balanced, obviously you can say that the average value is going to be 0. Whether you integrate and get it or whatever way. Just by observation you can say yes, because this is balanced, so average value is going to be 0. Now in this waveform, you try multiplying a sine wave. What you are going to get in effect is basically, say, because let's say this is 1 and this is going, so it will be basically a magnified sine wave, something like this. Sorry, this direction will change because both are negative on the other half. So this will be something like this. Understanding my point? So whenever you are trying to multiply this sinusoid over here, that means sine theta with this waveform, which is like equal in both the halves and symmetric about this, say, pi, what you are finding is basically rectified sine wave kind of structure, which means certainly in this case you are going to have some non-zero average value. Same thing if you try with cosine, the product with cosine, say this is your waveform, and you try multiplying something like this, what you will get? You will get basically a magnified version of the same cosine. So it will be this blue waveform. Now you see again in the two halves, this is basically same. Whatever positive negative value this is having here, the same is here as well. So what result you should expect from here? What DC value?
Sir, the second one also will get reversed, like in the second portion.
Yes, sir. After pi,
Yes, that is true. So this becomes maybe a jump on the waveform, but the, okay, something like this, right?
Yes, sir.
yes, sir.
So this becomes positive, whereas this is negative. Yeah, but the conclusion remains same, right?
Yes, sir.
You have the symmetric structure on both the halves. So basically what you will expect that a zero average value from this product. Everywhere we are trying to take average. That's why this 0 to 1 by 2 pi, 0 to 2 pi integration is there. Whether you take with VRO, theta, d theta, this means you are trying to take out the DC component. If you are trying to take out the sinusoids, or sorry, cosinusoids, which is AN, this is basically VRO, theta, cos n theta, d theta. If there is any cosinusoidal component available in this VRO, then you will have a non-zero value over here. And if there is any sinusoidal component in this waveform, VRO theta, sin n theta, so you will have non-zero value of Bn. Again, there is difference between when we talk about odd harmonics and even harmonics. See, odd harmonic will only have one half or odd number of this, odd to say like something like 4.5 cycles or 3.5 cycles or 1.5 cycles within one half cycle. This will not be integer number when you talk about odd harmonic. Understand my point? Say the frequency is 3 times. So you will have 1.5 cycle over here, 1.5 cycle over here. So the condition for odd is different, and when you have even, this will have, let's say, equal number of cycles, say 1 and 1 or 2 and 2. This is kind of integer number, what you are seeing over here. So these two also will behave differently. Now, how to identify what we are going to see in the waveform? So first and foremost condition, whenever you are going to take Fourier transform for any given PWM waveform, you must ensure that this waveform is repeating itself after every time period t or 2 pi, whatever you want to call it. This must be periodic. If this is aperiodic, you cannot take Fourier transform. This is the first rule. Because the sinusoid which you are trying to multiply, that is of some certain frequency, right? It is not just somewhere 50 hertz, somewhere 60 hertz and so on. So it must be repeating itself over the time period. Then you try to project your sine component over here, let's say the fundamental, on the PWM waveform, and you see that the positive and negatives are like kind of matching. So you can expect some non-zero value for this component. You understand my point? something like odd symmetric, even symmetric, this kind of waveform what you have seen. So whatever symmetry this is holding, this waveform also should hold the same symmetry. Okay, now same thing you can do with the cosinusoid. You can simply impose on this and you can see whether you can expect to get any cosinusoidal component or not. Because it's a lot of exercise, no? When you do Fourier transform, you have to compute lot of things. So beforehand, if you know few things, you need not compute all the components. Some components you can clearly knock off. For example, for this we can say that DC is 0. And then we can say that cosine is also 0 because the product is coming out to be balanced on both the halves. You understand my point? Any cosinusoid, whether it is even or odd, no, any frequency, this is coming out to be 0 because you have in the positive half cycle you have positive negative both, and here in negative also you have positive negative both. So it will cancel out. But if you talk about the sinusoid waveforms only, if you have only sinusoidal waveforms, in case of fundamental you are finding that positive is matching with positive and negative is matching with negative, and so you are expecting a non-zero value for B1. And because this comes in the category of odd harmonic, so same thing can be expected about 3, B3. So for example, just count the positive negative cycles or positive negative halves in each half cycle of this waveform VRO. So you have 2 positive and 1 negative over here, whereas you have 2 negative and 1 positive over here. So which means you are going to get overall product as 2 positive and 1 negative on the positive half cycle. And here you are going to get 2 positive and 1 negative on the negative half cycle. So overall you have some average value present in total. Some part is getting cancelled, of course, but it is not getting cancelled entirely. Just keep these observations in mind because I'm trying to take you towards something important, which is called waveform symmetry. Now, the same thing if you try with even order harmonic, let's say sinusoid only, what will happen? You have, say, 2 cycles on both the sides. Now what is happening? You see, you have equal positive, equal negative on this side and equal positive, equal negative on this side. So overall, this is cancelling in itself. If these values are equal, then for this waveform, the sum or the product of the total is also going to be equal for the positive and negative half cycles. You understand the point?
Yes, sir.
Are you able to visualize this?
Yes, sir.
Yes, sir.
Yes, sir.
So trying to say is that if you have similar structure on the positive and negative side and you try to multiply with any even harmonic, what result you are going to get is 0 component for that. Understanding my point? So these are very, very important features what your PWM waveform should have. Now, for example, if I talk about, let's say you are generating PWM waveform. Now, what all properties it should hold? So first and foremost property what we have seen is that it must be periodic with respect to certain frequency. It must repeat itself. So then only you can have a fixed fundamental for this waveform. This is the first requirement or first property for the waveform, and this property is called full wave symmetry. If you ensure this, that means you are ensuring a fixed fundamental. If you are not able to ensure this property, then your waveform itself is not defined. It is aperiodic. You don't have any fundamental frequency over there. You understand my point? So this is the first condition. Now, the second condition which I have been talking about.
Sir, why you add a full wave?
Yeah, because this is full wave.
Okay, yes.
Now, second observation what we have seen, that if we have similar structure but with no opposite polarity, let's say I have a waveform something like this here and another cycle is something like this here. If these two structures are exactly symmetric, no, let's say symmetric and opposite. So if I write this as VRO theta, then I am having exactly opposite VRO over here, which is pi plus theta. And this symmetry should be about this pi axis. So rather it should be pi minus theta, and you go on the other side as pi plus theta. So if you move equal angles on both the sides of this middle or half cycle, you should see exactly opposite values of the VRO. Then in that case, we can ensure that if you are having even harmonic multiplication with this will cancel out to be 0. So if waveform is containing this kind of symmetry, there is guaranteed to be no even harmonics, because it will exactly cancel out whatever you are having on both the halves, what we have seen for the square wave. This property is called half wave symmetry. And definition for this we can write mathematically as this: VRO pi minus theta minus of VRO pi plus theta. You move equal angles about the half cycle and you should see exactly opposite values. Correct? The previous one we can write mathematically as VRO theta is nothing but VRO 2 pi plus theta. After every 2 pi you have exactly same value. And this I am talking about steady state operation, of course. So this property must be fulfilled. This property must be fulfilled. So if we keep these kind of things, we can ensure that we have a fixed fundamental, and here even and also the DC, these both are going to be 0 if we maintain half wave symmetry. Understanding my point? Are you able to visualize that?
Yes, sir.
Okay, so let's stop over here. You move to next class. We will continue the discussion from here in the next class.
Thank you.
Okay.
Thank you, sir.
Thank you, sir.
Thank
Thanks.
you.